All right, guys. We're going to be using Stokes' theorem to evaluate the line integrals f dot dr for each one of these boundaries on the triangle here from 6, 0, 0. Let me zoom in a little bit. 0, 6, 0, and 0, 0, 6 oriented counterclockwise as viewed from above. So what do they mean by this? They mean that we're definitely going in this direction across our surface counterclockwise. If you wanted to, you could find this trace and do the first line, that's C1, right? I'm not going to be doing that in this video. We will be doing the double integral, however. We're going to be using Stokes' theorem to do that. And then you've got C2, that's this one, by using Stokes' theorem. And then Cn here is going to be our C3. I will do that in a second video. In this, we're actually going to be finding the normal vector in this video to utilize that, and then find an equation of the plane, so we have our limits of integration that we're going to need. And then we're also going to, from that equation of the plane, find our mixed partials with respect to that. And from that, find the normal vector once again. Why do I do it twice? Well, one's for accuracy, one's for the theorem to show you how it works, and secondly, it's kind of to show you how three-dimensional surfaces are changing with respect to their mixed partials. So you're getting a lot out of this video if you pay attention to exactly what I'm doing, even though I'm doing a calculation twice here. It seems redundant, but I'm a very accurate person, so I want to make sure that y'all understand it as well, and we get extra bits of information out of it. So when we're doing this, we need to find our vectors. In order to do that, we need to find our changes for each one of these lines here. So with the first boundary, we're going to be doing 0 minus 6. We're finding the vector QR. And then 6 minus 0 and 0 minus 0. All right, now that's going to be QR is equal to negative 6, 6, and 0. Now pause the video if you need to see how I did that there. Now for QP, it's going to be 0 minus 6, because we're going in this direction. Now, why am I going in this direction? If we're doing counterclockwise, why would I do that? Well, in order to get the right vector, to get the right positive orientation, I know that I need to be crossing it with this direction of the vector that I'm establishing, because I'm establishing the basis in free space here, not the grid. So that means I'm forcing this to be QR, right, crossed with QP, and that gives me a normal vector in the orientation that I want to pick, right? I won't get into the minutia of why that works, but do not, whatever you do not do QP, right, mixed with that, because you're not going to get the right, that's nonsense, right? These are linearly independent when we cross these by definition. If you dotted them, it would be 0, correct? Let's see. Negative 6 times negative 6 gives you 36. 0.06 is 0. 6 and 0 is 0. Let's see. Is that right? It's 6, 6. 6, 0, 6. Actually, we do get a scale. We get 36 scalar. Well, the point is that you want to make sure your directions are accurate here. We're establishing the basis. That's what I meant. I added that at last bit. I guess that's not correct. I guess I can't use that theory to explain that. But I can tell you for, very accurately that if I want positive orientation, I need to do the proper direction of my vectors. In other words, you're establishing the direction here. Hopefully that makes sense. I spent way too much time talking about that. But now that we have that, we're going to get the proper orientation facing outward as viewed from above, not inward. So I'll do my cross product, and remember, guys, there's this sign chart for properties and matrices, our jth component. So for your ith, you're going to get 6 times 6 minus 0 times 0, that's 36. Negative for your jth component, remember, that's the property of that matrix. And that's going to be negative 6, 6 is negative 36 with that negative here for the property of the matrix, and that's 36 positive and 36. You get 36, 36, 36. And then now that we have this, we can dot it with some initial point that I pick on the grid using our equation of the plane algorithm here. or what we're using to find our equation of the plane. So we're going to take this normal vector, and we're going to dot it with some x minus x initial, y minus y initial, z minus z initial. Okay, the only way to really do that, the only points we really know here are P point, Q point, and R point. I picked X. It's the easiest. It's the first one that starts out. You could probably use the other ones, but I would stick to this. And so you likely can. I would experiment with it. But that's going to be X minus 6, Y minus 0, Z minus 0. So when you do this, you end up just getting this dotted with that X minus 6, Y, and Z. So it's going to give you 36, 36, 36, because that's your normal vector. And you're dotting it with your algorithm here. I can just put change in X, right, which is X minus 6. Change in Y, change in Z. Just save writing here. So that's change in Y is Y minus 0 yet again, Z minus 0, and X minus 6. Now that I have this, you actually end up getting what follows here. Now I'm going to do all the calculations out here. So give me a second. All right, there's that. We're good. Let's zoom in a little bit. All right. You're going to see why I did this in a minute. So 36x minus 6. Not a comma, sorry. And then plus 36y plus 36c is equal to 0. All right. So the next thing you want to do is get rid of that 36 scalar, right? So that's why I'm doing this. So all we really have to do for that, guys, is just divide by that 36. Let's do that. All the way through, including the 0, stick to form. So that's going to leave us with what follows. And I'm going to go ahead and drag and drop because we're going to run out of time otherwise. That leaves us with this equation here. X minus 6 plus y plus z equals 0. So now you need to solve for z. All right, because we need to find that equation of the plane. So in order to find the equation of the plane, all you have to do is solve for z here, and let's see what I can do here. It's going to give you z is equal to minus x minus y plus 6. Cool. Now, we only have the equation of the plane. But remember earlier how I mentioned that I wanted to find my mixed partials with respect to that, to the parametrization of the surface. All right. Well, the reason I'm doing this is because if you, let me go this way a little bit. I want to show you why. Let's take this image here, bring it down. Let me show you what's going on. So I need to find, now that we have our equation of the plane, which is this whole thing, right? This image here. What I'm doing now is I'm showing you the proper circulation, taking the mixed partials of that surface. So you can see, right, that we've got our SX, right here, crossed with our SY. Now we have, at any point on here, the normal vector, by definition of the normal vector, on that surface. And so what I need to do here is I need to find my surface parametrization. Well, that's easy. Because all you really need to do in that case is let x, so let me go ahead and write it out. So the parametrization of your surface. I'm used to people interacting with me, so I know these tutor videos starting out, I just started making them, are going to be a little fuzzy. But your parameterization is we're going to let x equals x, and we're going to let y equal y, and we're going to put our parameter for z in here, which was, what was that when I got over here? Okay, the 6, yeah. 6 minus x minus y. Now, the reason we're doing this is because we're taking the mixed partials with respect to x and y. We don't want any zth component in there. That's why you set your z equal to this in here. So now, then we take the mixed partial with respect to x. You get 1. So let me write this out for x. We know this by now. Mixed partial with respect to y is 0. You can also view that as dx if you want. That's 0. And this is negative 1 dx again, right? Don't worry about the dx and dy. Just work through the algebra. You will be getting a surface area element change in ds here. They call it, but it's also referred in some books as dA. That's fine. So then let's go ahead and write this out. We're going to find our normal vector yet again, just to get through all the mixed work here, right? We're just going to end up getting the same vector back that we started out with, but without the 36. Good grief. So my ith is just going to give me 1 here, right? So that's minus 1 is 1. And then jth, minus 1 is 1. And then kth, 1 minus 0 is 1. So yeah, we got this back. But instead of winding with 36, 36, 36, right, I ended up getting 1, 1, 1, eliminated the scalar. I do it this way. You can try it to see if you get the right answer. Doing it that way with the 36 is without defining the parametrization of your surface. But I find it much better to do it that way because you can see what's changing, albeit the SX and the SY on that surface at any point. And it's useful with this common example to other applications of different surfaces like spheres, paraboloids, whatever the case may be. So we got our SX and XY. We got our little DS element here, or our normal vector. I just crank it back out as the normal vector, guys. You don't have to stick to notation like that. Don't let that overwhelm you. So now we need to find the curl. So let me zoom out a little bit. I'll try to be as quick as possible. All right. So I went ahead and did the set up the calculation kind of ahead of time. Let's go down here. All right. All right. So for your curl, we're going to use the vector field that they gave us. And we're going to work on the mixed partials. Guys, it's the same thing for finding exactness, only in 3D. So you are doing the determinant here. Now, your ith component is going to be the change in y with respect to y, which is going to give you 0 for that component, right? And then the change in z, which is going to give you a minus 2z here. And don't let that freak you out. You will get a negative 2z here. That's fine when you're doing the curl, right? We're not worried about orientation with this, guys. We're just simply working on the curl here. So don't, that arrow's not going to go away. So don't worry about the sign for your field. That doesn't matter. What matters is the orientation of your surface. So I want to make that abundantly clear. Now, when you're working on the y component, there's already a negative involved, but that's a negative 2x then, right? Minus rho z here. The mixed partial with respect to z on x and y is just 0. So you just end up getting, once again, negative 2x because of the property of matrices. Remember, this always stays. So that negative is already understood in there. So you might be tempted to be like, it's positive 2x. Well, it's not because you're working on the jth component. All right. It's easier to do that than to use that laser. The laser slows things down. So now your kth component, you're working on x here. Guys, that's going to be 0 with a mixed partial of these two signs, y and z. And then minus 2y here. Because of the y squared, the 6x is just 0 with the mixed partial with respect to y. So you're going to end up getting minus 2y here, right? Let's see if I did that right. Did I do that right? Is that? Yeah. Minus 2y. All right, now we found our curl. Let's curl up. Now, I'm just going to set the integral up. Guys, I'm going to leave it to you to do the calculation. I can do a calculation in another video. And the reason why is these got to be timely. But rest assured, this has been checked, right? And this is correct. So there's one last step I'm going to show you, and that's your limits of integration, but give me a moment. So we're going to put our curl in right here. I guess I should stick to form, right? Let's go ahead and do that. Curl operating on f, dotted, ds or dA or n, however you want to see that. It's nothing special. So then that's going to end up being what we have here. I'll show you the limits of integration. We'll call it a vid. Stuff. All right. Now, for your limits of integration, and I'm going to show you all this in Mathematica, so that way y'all can see that this is in fact correct here, and you should be getting 216 for this. But for your equation of the plane, right, for your limits of integration, right, and I'm going to make this clear here, right, your limits of integration, we knew that x is changing in this direction from 0 to 6. We know that y is changing from 0 to 6 minus x. Remember, guys, this is a double integral. Nothing's changed there. So your change in y is going to be from y is equal to 0, right, to y is equal to 6 minus x. I'll make that clear here. This is the line y is equal to 6 minus x. That's the upper boundary. Ooh, sorry. And that's going to be from y is equal to 0 to that, right? So we know how to do double integrals. And x is just 0 to 6. Right. Because we're working on that integral. And those are, yeah, double integral, right? We know how to do that. So 0, 6 minus x for the surface z. And that's it, guys. You should end up getting 216 for this. Let me go ahead and bring Mathematica over to the plate. So I did promise y'all the algorithm. All right. Made this little program myself here. I'm not a programmer, but it's really useful. So if you want to pause the video, if you waited long enough, you get the prize, and there it is. So make sure you have it in there, everything like I have it, right? There's your mixed partials. I used Rx, Ry, no big deal. I used R for my surface. You can do that too. It's just a letter. Crossing Ry, Rx. Don't worry about that. That's a Mathematica thing. And then I end up getting 216 here. Okay, guys, that's your, let me shift enter this so you do know it is in fact correct. And there we go. Positive flux. Or I have flux here, but positive curl. There you go, guys. And have a good night. If you have any questions, I guess leave it in the comments and whatnot. Have a good night. Bye-bye. Bye.